everyone. My name is Ren. Today I'm going to present my recent work on desensitization, privacy-aware, and tag-preserving crash reports. And this work is done in collaboration with my colleagues at Georgia Tech. So I believe most of you guys have seen it before, but if you don't need to raise your hand. And this is just the blue screen of death, which indicates a fatal error for your operating system, and which is probably unrecoverable. And at that point, you basically just have to reboot your system and hope that your data is still there. Unfortunately, that's not the only kind of crashes that you can see in your daily life. So besides the operating system crashes, there are also some application crashes where it can happen across trivial ones, from trivial ones to the browser, more complicated ones. And then also it can happen across platforms, including Windows, Mac, and Linux. And it can also happen in different situations in your daily life, and when you're retrieving money from ATM, or even when you're presenting. So we have some data about how many crashes that Firefox has, and we basically surveyed the latest stable version of Firefox and found that more than 200K of crashes in the past 7 days, which is around 30K of crash reports a day reported across different platforms for this single applications. So what is really happening for the current crash reporting system? So when a program crashes, it would obviously generate a crash report, a crash dump, and which is informative for debugging. And because it's informative, the developers will try to collect it from the user and then send it to the server end for analysis. On the developer side, when the crashes get collected, it will get bucketized for prioritizing certain bugs that's more severe based on the number of crashes that you can get, and and they will then dig into further for root causes. So such kind of a crash reporting system adopts the typical client and server model, and it's adopted by many major software vendors, including the Ubuntu, Microsoft, Mozilla, and so on. So what is actually a crash report? Obviously, it's a very informative piece to help developers for debugging, but at the same time, basically it's a memory dump that contains the last state of your CPU register and memory snapshot before the program crashes, and also collects some information such as the execution environment, such as the environment variables, the versions that you run, and so on. So there are basically two major formats. One is the coredump and minidump. Coredump is the one that basically contains everything that I just mentioned, but for minidumps, it just contains partial memory snapshot, which only focus on the stack regions unless specified. So what could go wrong here? So imagine all the crashes from the user end, and they are stored on the server side with all these kind of data on the server, and obviously there will be privacy leakage. And actually, there are many major incidents of data breaches happens recently, including those SSN leakage from Equifax, and also password leakage from Facebook. And this is definitely one of the concerns that we are talking about here, why we inspired the research. And one of the recent study actually tried to evaluate the impact of such kind of privacy leakage among the crash reports. And they basically surveyed the crashes that's public available online by the Mozilla, and they found that 2.5 million of crash reports actually contains private user data based on their simple pattern matching algorithms. So they found 20K of session tokens, 700 passwords, and also 9K of emails. And later, this source has been closed due to the similar privacy reasons. So that comes to the conclusion why we need privacy-aware crash reports. And simply, such kind of a private information is not only unwelcome for the users, but also for the developers. So for example, user obviously doesn't want to have the private information leaked, but also at the same time, developer doesn't want any storage breaches to their privacy sensitive reports, which might cause privacy bad publicity and as well as some financial liabilities later on. So there's already some existing solutions that may be proposed by researchers and developers, including one of them is manual annotation, which requires the developers to basically manually annotate those variables that might contain sensitive information. But at the same time, it's very time-consuming, it's very program-dependent, so you have to have the developers does all the job. The other one is the more general heuristic approach where it does pattern-based searching using regular expressions, such as trying to find the URLs and those kind of things. But it's very error-prone because sensitive information can take various forms and doesn't necessarily mean based on a simple form. The other one is the more heavy-lifted one. It's using the input logging. Basically, it tries to log the input that causes the crashes and basically replace those inputs bytes that's non-relevant to the crashes. But again, because it's heavyweight, using taint and symbolic execution, and also it's very incompatible to the current framework because it requires logging of the user input anyway, which is not compatible as we shown. So our proposed solution is called desensitization. Basically, we want to create a new crash reporting framework that's aggressively removing the irrelevant data to prioritize privacy. And still on the other hand, we want to contain sufficient information for developers to do effective bug and attack analysis. And also, we aim to have this framework be lightweight and sit on the client side and work for any application, even for closed source applications. So the key observation here is that rather than we want to focusing on identifying the sensitive data when program crashes, like what previous approaches have tried to do, we are basically taking from the server side in terms of surveying the existing crash analysis techniques and adopt some generalized features from them to basically record whatever they need, but meanwhile removing whatever that's not necessary for them. So we did some. Here's just a list of things, crash analysis and triage techniques that we can survey. And then basically there are 4 major categories, including the IP-based approach, cost-based, crash signature-based, as well as the fault-based. So actually most major software vendors, including Ubuntu, Chrome, Firefox, they adopt the cost stack and signature-based approach for bucketization just for the sake of easiness. And then desensitize, our work basically handles the first 3 pretty well. And for the last one, some other works also use the fault-based approach, which basically performs some lightweight reverse execution, which might be a little limited based on the number of instructions that can be reversely executed. Although our current work doesn't really support it, but we will discuss about this kind of a feature later on when we talk about the design. So. There are some existing anomaly detection schemes which we found, and basically there are also 4 major categories that they're looking into, including the heap metadata, program-specific structures, ROP gadgets, and shellcodes. So for example, Caviar is work that try to detect any invalid typecasting, and they basically use the pointers and program structures to detect such kind of anomaly situations. And for Dano and Hot Tracer, they use heap metadata and pointers to try to detect any heap violation, including use of free, heap overflow, etc. And also for RP scan, RP MU, they try to identify RP using the executed traces and so on. So although some of the schemes does not directly apply to the current framework, where we basically just get the last memory snapshot of the crashes, while at the same time there might be some runtime techniques, but we believe a lot of techniques proposed here can actually be applied on the server end for developers to find those situations. So here's just the overview of our framework, in which we adopt a modular design in order to be extensible. And basically when a crash happens, each module will take its sequential turn to identify what's necessary based on the information in the crash reports. And after everything has done, they will basically remove all those unnecessary information and save it as a sparse file in order to save some storage resources. And everything happens on the client side. That's why we have to design it to be as practical as possible. Here's a motivating example that we use to motivate our research. Basically, this is a simple program which it asks for user to intake a password, and then it allocates a dynamically allocates a string objects which store on a heap. But unfortunately, due to the string copy vulnerability, there's a heap overflow. And so it can basically overwritten everything that's inside the string object, including the function pointer. And so it does arbitrary execution, basically stack pivots with a bunch of ROP gadgets, and finally jump to the shellcodes. But attackers can make mistakes when they're calculating offsets due to randomization, et cetera, and so it crashes. So unfortunately, besides the heap regions that actually contains these kind of attack evidence and those kind of bug-related situations, there are much more data actually on the stack, heap, and other memory regions, including the password that user has inputted before. So how do we handle this situation? One of the modules we designed is for pointer identification. So in order to determine the pointer, we basically scan every 4 to 8 bytes and see if it points to a valid memory region or not. And furthermore, we can distinguish the co-pointer with the data pointer, and based on the proper access permission to the memory module. And these are information pretty much needed by the developers because, for example, for the co-pointer, it can be an indicator of return addresses, call stacks, callbacks, or implementation of polymorphism in the modern program space. And for the data pointer, obviously, it's heavily used these days in a modern area to point to some complex data structures to support some efficient memory access. And so if we back to the same motivating example again, if we back to the same motivating example again, it's definitely recording any ROP gadgets that's left in the memory space, and so along with all other pointers that's being reside in the memory snapshot. So the second module is actually the heap module, which we try to detect all the heap metadata resides in the memory space. And taking ptmalloc as an example, which is a commonly used allocator, it includes several key components for managing dynamic memory allocation, including arenas, beans, and chunk metadata, which indicates the status of the chunk. So if we take those knowledge into account, and the current module basically can record whatever that's considered as metadata, heap metadata, and leave those user data untouched as unidentified. And for the current module, we also support another popular memory allocator, JE-malloc, which is used by some software like Firefox. And the only difference is that they contain different locations for storage of metadata. And so we can easily handle those. So another module we designed is the one that tries to detect ROP chains, 4 chains. And for this module, rather than having a complicating, overlapping functionality with the pointer identification module, we try to aim for saving the non-pointer data in between the co-pointers, in between the gadgets. And we set a threshold basically of abnormal density for code pointers in certain memory regions, and try to identify a full chain of memory ROP gadgets, ROP chains. So back to the same example, we will save all the data in between the gadgets, which might be used for as for the developers, which are definitely could be some arguments used throughout the ROP chain. We also defined more modules, but due to the time limit, we're not going to cover it all. And all the details are in the paper. But overall, here are just the applicable scenarios that our tool can preserve useful information for debugging various bug types. And for the current work, we're definitely not arguing for the completeness, but instead, we just want to provide a friendly customization for developers so that they can later on customize it based on the domain knowledge by adding a module. So if we go back to the same reverse execution situation we discussed before, we can easily have a developer add a module to preserve the data near the crash sites on the stack due to the limited number of reverse execution that can be done in reality. So also the developers, another example is that the developers can basically identify certain call frames that might be more error prone or critical, and then they can basically customize it in order to preserve more information on those rather than the other call frames. So in terms of the experiment setup, we did, it's one of the hard problems is try to find the open crashes as we discussed. Open source crashes, as we discussed, because of the privacy issue. And so we basically collect all the POCs towards CVEs, and then we use fuzzing to find it, to collect more. Basically, in total, we collect more than 13K of crashes from various benchmarks, including FFmpeg, PHP, Chocolate Core, Firefox, and also including the crashes caused by the DEF CON CTF. So among them, there are two categories. One is the normal crashes. The other is the attacker-driven crashes. The normal crashes doesn't involve any exploit behaviors, but at the same time, the other one involves is actually caused by the failed of 4-chain exploits. So in terms of evaluating the privacy awareness of the current approach, we measure the distribution of memory bytes that can be desensitized. And basically, we found that we can remove actually 80% of the bytes based on our current approach, but less effective for the minidumps, simply because minidump only preserve the stack regions, which are more control relevant rather than user data storage. And for the rest that has been remained in the crashes, pointers dominance, and the heap metadata becomes the second factor in terms of playing the role. So to further evaluate it and understand the meaning of the bytes that we removed, we count the printable strings as a proof of concepts. And so we just use it as a proof of concepts in terms of measuring what are the privacy issues that we might face. And we found that we can actually remove 95% of the strings in the core dump and less effective for the minidump as well. So here's just an example of a simple example of a source of leakage in. Oh, I see.
Program chair is here for the closing remarks.
Okay.
Sorry.
Okay. Yeah, that's fine.
No. I mean, conclude the talk.
Oh, so we actually did find some privacy leakage issues in the Firefox based on their implementation, and even in their minidumps. And we also provide some benefits for file size reduction, as well as we are basically practical. So yeah, that's conclusion. And
all right.
Yeah.
Thanks, the speaker.
Thank you.